I'm Seema and welcome to part 25 of the chapter Thermodynamics. In this video, I'm going to solve 3 numerical problems from your NCERT textbook exercise, that is from chapter 6 Thermodynamics, question number 10, 11 and 12. Not wasting any time, let us start with the first question. The question reads that you have to calculate the enthalpy change on freezing 1 mole of water at 10 degrees Celsius to ice at minus 10 degrees Celsius. The enthalpy of fusion is given to you, which is equal to 6.03 kilojoules per mole at 0 degrees Celsius. The specific heats of water in the liquid state and in the solid state are given to you. This change takes place in 3 steps. It is not, although the temperature change may appear to be continuous, in between there is a time where the water turns into ice, and in all that time that the water is converting into ice, the temperature of the water remains at 0 degrees Celsius. And at this point it is losing heat, but this heat, there is no change in temperature. It remains at 0 degrees Celsius and the liquid, it turns into solid. This process takes place in 3 steps. In the first step, we have water at 0 degrees Celsius, water in the liquid state at 10 degrees Celsius, and it has to be brought down to 0 degrees Celsius in the liquid state. So in the first step, water which is in the liquid state at 10 degrees Celsius comes down to water at 0 degrees Celsius. So let us write down the steps. In the first step, you have water, liquid, which turns into, at 10 degrees Celsius, into water, liquid, at 0 degrees Celsius. Okay? So the temperature change is from 10 to 0 degree Celsius. And delta T, therefore, what is the difference in the temperature? Is minus 10. The temperature difference is, why do I put a minus sign? The temperature is decreasing by 10 degrees. 10 degrees Celsius or 10 Kelvin means the same thing, because the measure of a degree is the same. So the temperature difference is of 10 degrees Celsius or 10 Kelvin, and we put a negative sign for delta T, that is the change in temperature, because this is temperature which is decreasing, right? So what is happening in the first step? You have water in the liquid state which turns into water in the liquid state, but only the temperature is changing. The water is cooling down. Now what happens in the second step? At this step, if you have to calculate the enthalpy of this step, how would you do it? You will calculate the enthalpy of this step, and you'll say that what is the enthalpy? You can calculate by, we know that Q is equal to NC dt. We'll use this formula. Here enthalpy change will be equal to Q because there's no work being done here. So NC dt is the formula that we use, where N is the number of moles of the substance that you are, when you bring about a temperature change, how much temperature change takes place, or how much heat has to be given or is given out, is calculated by Q, which is the amount of heat, and N is the number of moles, C is the specific heat of that particular substance which is being heated or is being cooled, and delta T is the amount of temperature change that takes place. That is what is the thermometer reading initially and later. So using this formula, in the first step, that is, we'll call it delta H1, right? In delta H1, what happens? Q is equal to N, number of moles is 1 mole, C is the specific heat, and specific heat of water in the liquid state, and the specific heat of water in the liquid state is given to us as Cp. Water, liquid is 75, so 1 mole into 75.3 joules per Kelvin, per mole per Kelvin, into, let me just write it here so that I can write the units also. Delta H1 would be equal to, Q is equal to number of moles. There is 1 mole into the specific heat of water in the liquid state is 75.3 joules per mole per Kelvin, into the difference in temperature is a decrease in temperature by 10 degrees. Therefore, we'll write the difference, the decrease in temperature, or delta T, is minus 10. And the temperature is in Kelvin, right? So minus a difference of minus 10 Kelvin takes place. The reason why I've written the units here is that we are looking for delta H, and in delta H there is no work being done, so we are looking for the unit of heat, which is joule. Therefore our answer should be in joules. That always, when you always write down the units and you cancel out the units and you get the correct units, that is an indication that you've plugged in the right values and you've arrived at the right answer. So here, mole and mole inverse get cancelled. Kelvin inverse and Kelvin get cancelled. So you're left with joules, which means we have plugged in the right values. And what does this value delta H1 come out to be equal to? This would be 753 joules, right? This would be equal to 753 joules. Now, this was the first step. What happened in this? That we had water in the liquid state at 10 degrees Celsius, and we reduced the temperature of water to 0 degrees Celsius. Now we come to the second step. In the second step, what happens? You now have water. In the second step, you have water, liquid at 0 degrees Celsius, which comes down from 0 degrees Celsius. It remains at 0 degrees Celsius, and it turns into water in the solid state. Now, what exactly is happening in this step? The physical state of water is changing from the liquid state to the solid state, and it is releasing heat in order to, the attractions between the molecules of water are increasing, and water from liquid is turning into a solid, but the temperature at this point becomes constant. Although it is releasing heat, yet you cannot observe a difference in the temperature. Therefore, you cannot calculate Q here, because Q, since delta T is 0, you will not be able to notice any change in the heat. But heat is being given out, and to calculate that heat, we use the enthalpy of fusion. And this heat is actually known as the latent heat of fusion. Latent means hidden. The only way how we can see that heat is given or given out by a substance is by noticing the change in temperature. But in this case, there is no change in temperature, but we know that liquid water is turning into solid, so the attractions between the molecules are changing. And if the attractions are changing, there has to be some energy change which is occurring. So a measure of that is done by, and this amount, the enthalpy of fusion is also fixed for different substances. So enthalpy of fusion of water for 1 mole is, it is given for 1 mole is 6.03 kilojoules per mole. And since we have only 1 mole, you can calculate this as the second enthalpy, the enthalpy of fusion for water. What is happening in this step? Let me repeat. Water in the liquid state is turning into water in the solid state at 0 degrees Celsius. There is no change in temperature, right? And therefore we consider the second enthalpy to be the latent heat of fusion of water, and it is 1 mole into latent heat of fusion is given to you, which is 6.03 kilojoules per mole, right? Now we have been given this value in kilojoules, but we calculated the value of delta H1 in joules. So we should always, if we have to add them, we should always have the same units. So what are we going to do? In this step, we are going to convert it into joules. So this would be equal to, if you multiply it by 1000, you'll get the answer in joules. You'll convert kilojoules into joules. So it would be 6030 joules per mole, right? And here also, if you really see, since we had only 1 mole of substance, you could call this joules per mole as the unit, right? So you get joules per mole, 6030 joules per mole would be the latent heat, and this is your second enthalpy. Now in the third step, what happens? The third step is where now you have water in the solid state at 0 degrees Celsius, and you're turning it into minus 10 degrees Celsius, and you're turning this water, that is ice, into solid ice at minus 10 degrees Celsius. So now you're converting in the same physical state. We are turning the solid ice, that is solid ice, and we are reducing the temperature of the solid ice. And at this point, again, there is a temperature change which is occurring. So we'll use this formula. What would be the enthalpy here? We'll call it enthalpy 3. The third enthalpy, that is, it would be number of moles is 1. And what is the specific heat for solid water? That is ice. It is 36.8 joules per mole per Kelvin, right? And what is the temperature change? Again is minus 10 Kelvin, right? The minus, so you'll get the temperature in a negative value. And one more thing here. Since delta H fusion of 6030 would also be negative, it should also be negative because this is also the amount of heat that is being given out. To convert, it is, if the attractions are increasing, it means energy is being given out. More stability is being acquired by water. So this would also be a negative value. And this would now become 2. This would be 368 minus 368 joules per mole, right? I just put the per mole and I did not write the mole here because I want all the units to be the same. So although you had the mole here, we can, since it is for 1 mole, the calculation is for 1 mole, I'm writing the per mole here so that we have the same units. Now, what has happened? We have carried out the process in 3 steps. And according to Hess's law, when a process takes place in a series of steps, the final reaction or the overall reaction is actually the enthalpy of the overall reaction is the sum of the enthalpies of each of these steps. So we see what is the overall reaction. We started with water liquid at 10 degrees Celsius and the final product was water which is a solid at minus 10 degrees Celsius, right? So water at liquid at 0 degrees Celsius was formed here and it was used up here. And here water solid at 0 degrees Celsius was formed here and it was used up here. So ultimately you are left with water liquid. You started with water liquid at 10 degrees Celsius and you ended up with water solid at minus 10 degrees Celsius. So we'll add up all the enthalpies. So enthalpy for this change will be equal to delta H1 plus delta H2 plus delta H3, which would be equal to, what is delta H1? 753. It will be a negative value, I'm sorry. Since it is heat being given out, all the values are negative. 7 minus 753 joules per mole minus 6030, we are actually adding it, let me write this, minus 6030 joules per mole, plus, we are adding it, so it plus, what is the value? Minus 368 joules per mole, right? So when you solve this, what is the answer that you get? You get minus 7151 joules per mole, right? So this is the enthalpy of this reaction. What was the question? You have to calculate the enthalpy change on freezing 1 mole of water at 10 degrees Celsius to ice at minus 10 degrees Celsius. So we have calculated the enthalpy change in freezing water from 10 degrees Celsius to ice at minus 10 degrees Celsius. We'll now come to the next question, that is question 6.11. So now this is question 11 and let me read the question. The question is that enthalpy of combustion of carbon to carbon dioxide is minus 393.5 kilojoules per mole, which means when you burn 1 mole of carbon to form carbon dioxide, to completely burn that, the amount of heat which is given out is minus 393.5. How do we say given out? Because the sign is negative, and as it is when something burns, heat is given out. You have to calculate the heat released upon the formation of 35.2 grams of carbon dioxide from carbon and oxygen gas. Let us first write down what is given to us. That enthalpy of combustion of carbon is given to us. That is what is the equation for the combustion of carbon? You have 1 mole of carbon, it combines with oxygen to form carbon dioxide, right? So this is completely burning in oxygen to form carbon dioxide. And what is the enthalpy here of combustion? It is minus 393.5 kilojoules per mole for 1 mole. right? Now the question is that you have to calculate the heat released upon the formation of 35.2 grams. Now this is not mentioned in moles, and our equation was a molar equation. We were talking in terms of moles of carbon dioxide. When 1 mole of carbon burns in 1 mole of oxygen, it results in the formation of 1 mole of carbon dioxide. Now the question is that how much heat will be released when you have these many grams of carbon dioxide being formed from carbon. So here we'll be using the mole concept. So what is the molar mass of carbon dioxide? The molar mass of carbon dioxide is, carbon is 12, oxygen is 16, and 16 into 2 is 32. Therefore, the molar mass of carbon dioxide is 44 grams. Which means that when you have 1 mole of carbon, the number of grams of carbon dioxide formed is 44. Or we can say that for 1 mole of carbon dioxide weighs 44 grams. So what would the number of moles be for 35.2 grams? Let us use unitary method. 44 grams of carbon dioxide makes 1 mole, right? So 1 gram of carbon dioxide of CO2 would make how much? 1 upon 44. And 35.2 grams of carbon dioxide will make how much? It would be 1 upon 44 into 35.2 moles. The grams and grams, mole, right? So the grams and grams get cancelled. You will get your reply in answer in moles. The number of moles would be 0.8 mole. It means that carbon dioxide, these many 35.2 grams of carbon dioxide is how many moles? Is 0.8 moles. We know when 1 mole of carbon dioxide is formed, the amount of heat produced is minus 393.5 kilojoules per mole. For 1 mole CO2, the enthalpy is, delta H is how much? It is minus 390, it is minus 393.5 kilojoules per mole. So for 0.8 mole, how much would it be? It would be minus, delta H would be equal to minus 393.5 kilojoules per mole into 0.8 mole, right? We have, for 1 mole, it is this much. For 0.8 mole, it will be into 0.8, right? Which would be equal to, how much would this heat be equal to? It would be equal to minus 314.8. Minus 314.8 kilojoules of heat, right? This would be the enthalpy. Now the mole is cancelled. So this would be the amount of heat which would be released in the burning of how many? In the burning of 0.8 mole of carbon. Why do I say 0.8 mole of carbon? Because when we used 1 mole of carbon, we got 1 mole of carbon dioxide. So in order to get 0.8 mole of carbon dioxide, how much carbon should you use? 0.8 mole. It's just understanding the entire reaction in terms of the mole concept also. So this was question 6.11, and let us now move to the next question, that is 6.12. What is the question? It reads that enthalpies of formation of carbon monoxide, carbon dioxide, N2O and N2O4 are minus 110, minus 393, 81 and 9.7 kilojoules per mole. These are the enthalpies of formation of these 4 compounds, respectively. You have to find the value of the enthalpy of reaction for this particular reaction. So an equation is given to us. We are supposed to calculate the enthalpy of reaction. Let me remind you, how do we calculate the enthalpy of reaction? The enthalpy of reaction is calculated by the summation of enthalpies of the products minus the summation of enthalpies of the reactants. The total sum of enthalpies of products minus the total sum of enthalpies of the reactants. Which enthalpies? Enthalpies of formation of each of the substances in their standard states. And that is the reason why these have all been given to you in the standard state, that is their gaseous state. You can use this data of enthalpies of formation only to calculate the enthalpy of reaction only when you have all the substances, that is the reactants and the products, in their standard states. It is only then that you can rely on the table, right? So since we've been given all the values, what are we supposed to do? We're just supposed to plug in the values and you find out the enthalpy of reaction would be equal to the summation of enthalpies of products minus summation of enthalpies of reactants. So let us write down the enthalpies below these first, right? N2O4. N2O4, what is the enthalpy? N2O4 is 9.7, right? And how many moles do we have? We have only 1 mole. I'm not writing the units here. It's all kilojoules per mole. So, carbon monoxide. Carbon monoxide is the first one. It is minus 110. But how many moles of carbon monoxide do we have? We have 3. So, it will be into 3. Right? This is the total heat of here. This is the total enthalpy of formation for N2O4. For N2O, it is, for N2O is the second, is minus 393. Right? And that's it. Since there's only 1 mole, we're not multiplying it by anything. And carbon dioxide is how much? Carbon dioxide is the second one. So, so this was N2O was the third one. That is 81. So this should be 81. This should be 81. And not the best way to write down a question. It would have been better if the names were written with it. So, and the carbon dioxide is minus 393, and since there are 3 moles, it will be into 3. So this is the total heat that we enthalpy of formation of each of the reactants and products according to this molar equation. One more thing, before we started solving this problem, we should see whether the equation is balanced or not. And we find that this equation is balanced. And now, what are we supposed to do? We have to find out the enthalpy of reaction. And what is it equal to? It is the summation of enthalpies of products, enthalpies of formation of products, minus the summation of enthalpies of formation of reactants. Right? So now let us plug in the values. What would the enthalpy of reaction be equal to? It would be the sum of, that is the enthalpies, let us do this, the enthalpy of formation of N2O, right? That is 1, plus, that's the product, plus the enthalpy of formation H of CO2, right, into 3, because there are 3 moles of this, minus the summation of enthalpies of reactants. This will be the enthalpy of, we'll first put the other bracket here, enthalpies of formation of, enthalpy of formation of N2O4 and plus, we are adding this, it is a negative value again, but enthalpies of formation of carbon monoxide into 3. Why? Because there are 3 moles of it, and that's it. So now we plug in the values. This would be equal to, what is the enthalpy of formation of N2O is 81, right? 81 plus, and it's a negative value, plus minus 393 into 3, and that is the products, minus, we have to subtract this, minus the enthalpies of N2O4, that will be 9.7, plus, it is again a negative value, minus 110 into 3. right? Now when we solve these, what do we get? We get minus 1098 minus 1098 is what we get here when we solve this, minus, and when we solve this we get minus 320.3, minus 320.3. And when you solve all of this, the answer you get is minus 777.7 kilojoules per mole. I'm writing down the unit here because I just avoided it since we were not cancelling out any units. So the enthalpy of reaction, or delta RH for this reaction, would be minus 777.7 kilojoules per mole. So these were 3 numerical problems from your NCERT text. In the next video, I'm going to solve the next 3 numerical problems. That will be question number 13, 14 and 15, and that would finish all our problems in the NCERT textbook based on enthalpies. And then in the succeeding video, we'll move on to entropy or spontaneity. Well, if you found this video helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.